Oh, okay, so it's recording. Yeah, sorry. So the last lecture, I could not finish it on board. Actually, I did finish, but it was not recorded. So it's just half an hour left. So I'm going to record it on Zoom and then post it. I hope this is the last time that this happens. So let me share just a couple of pages that are left I have. So share screen, where is share screen? Okay. There it is. Okay, now share. Okay, there we are. Right, so let me go to full screen mode. That's where's full screen? Yeah, there it is. Let me go to full screen mode. Yeah. Okay, so there we are. Okay, so what we have to do now is to construct products of all L functions with respect to all characters. And this new sort of generalized L function has some nice properties. And eventually, this will help us to show that the L functions or L series for non-trivial characters, their value at s equal to 1 is non-zero. And that's the crucial thing in the proof. So again, as before, let's fix an integer n bigger than or equal to 2. So Gn is the modular group. It's the group of invertible elements in the ring of integers modulo n. And let's look at this Zn or Xn. I guess it should be called Xn, but my notation is not very precise here. So this Xn of S is product of all L functions with respect to all Dirichlet characters on Gn. Now, the first thing we want to know is that this Cn has a nice form in the sense that Cn of S is equal to product of 1 minus p to the power minus f of p of S to the power minus gp, where f of p is the order of the cyclic group generated by the prime p inside this group, modular group Gn. And Gp is the index of this subgroup. So it's Gn divided by order of p, order of Gn divided by order of p. And moreover, this is crucial, very crucial. We want to see that this is a Dirichlet series with non-negative integral coefficients, which is convergent in real part of S bigger than 1. So we can write this as, the proof goes like simple. We can just write it as product of all L functions. Then we use the Euler product formula for each L function. And then we notice that, of course, chi of p is 0 if p divides n for all characters modulo n. So only those primes that do not divide n remain. Okay? So we switch the order of p and chi then we get this is equal to product of over all primes that do not divide n times product over all characters 1 minus chi p, p to the minus s inverse. Now each of those factors, we can write it, of course, using the previous lemma as 1 minus p to the power minus fps minus gp. So now, the nice thing about these factors is that each factor is manifestly a Dirichlet series with positive integral coefficients. If you raise it just to power minus 1, you just use geometric series. You see, f of p and g of p are integers, positive, non-negative integers. So that's it. So we have now this claim that we wanted to prove. Now, here is the crucial theorem. Now, this is the major theorem now. So it has two parts. First part says this CNS has a simple pole at s equal to 1. And the second part is the golden theorem that we need. I always mention that this is what eventually is going to be needed, namely L of 1 and chi is different from 0 for any non-trivial character. So, of course, L of 1 and chi 0 at a trivial character, there's a pole for that L function. So, but it's interesting that if chi is not the trivial character chi 0, then the function, the L series is defined at that point and is non-zero. So let's see how this goes now. Can I move this? Okay, yeah. So, yeah, I can see that some parts are missing on the top. So the previous function now, using the decompositions, we can write it as L of S and chi 0. And then L of S and chi 0 can be written as zeta of S times f of S. We have seen that before. So the Riemann's zeta function appears in the product. And then we have product over all L functions for non-trivial characters. So zeta, we know that it's originally defined for real part of S bigger than 1 and has a pole, simple pole at S equal to 1, but can be analytically continued to real part of S bigger than 0. This already we have seen. Okay, so now we can just say that if L of 1 and chi is different from 0 for every chi different from chi 0, then this product of these three terms has no chance of to be regular at s equal to 1, because the product of L functions for non-trivial characters is not 0. F of S at s equal to 1 is not 0, but zeta has a pole. So then it implies that in that case, we would have a simple pole at s equal to 1. So it just shows that if we prove that part B, then part A follows. So we're going to focus on proof of part B. Namely, we want to show that all L functions for non-trivial characters, their value at s equal to 1 is not 0. Okay, so the proof, again, is by contradiction. Suppose L of 1 and chi is equal to 0 for some chi different from 1. Now, so what does this show? If L of 1 and chi is equal to 0 for some character, non-trivial character, then that 0 is going to cancel the pole of zeta at s equal to 1. So the product, namely zeta ns, is going to have analytic continuation all the way to real part of S bigger than 0. Okay? if one of these L functions vanish at s equal to 1, zeta n of s is going to have an analytic continuation on real part of s bigger than 0. Now, this zeta n is a Dirichlet series with non-negative coefficients. And so by a previous theorem that we proved, not only it has analytic continuation to real part of s bigger than 0, but in fact, it's originally convergent for real part of s bigger than 0. You see, that's important. It's not now. It's not a question of analytic continuation. It's the question that the original series, Dirichlet series, which is the product of those three or those many terms appearing in zeta ns, the product is originally convergent for real part of s bigger than 0. Now, this is going to give us a contradiction. And the way to derive the contradiction is to notice that there are these factors in zeta n of s, which actually makes it blow up before reaching to the line real part of s equal to 0. So specifically, if you look at zeta n of s, which is product of over r primes not dividing at that part of it, 1 minus p minus f of ps minus gp, then there is this factor 1 minus p to the power minus fp of s to power minus gp. So again, using geometric series, we can write it as equal to 1 plus p to the power minus f of ps plus p to the power minus 2f of ps, and so on to the power of gp. Now, this series dominates term by term the series 1 plus p to the power minus phi n, but phi is Euler phi function, totient function, s plus p to the power minus 2 phi n s, so to the power of gp again. And the reason for that, of course, is that f of p, which was defined to be the order of the cyclic group generated by this prime p inside Gn, is obviously less than equal to Gn itself, order of Gn itself, which is phi of n. So from this domination, then you can go on and show that, I don't have notes here, you can go on and show that actually you can construct a series which specifically is going to blow up at s equal to 1 over phi n. And this series that we have, 1 minus p to the power minus f of ps minus gp, is bigger than or equal to that, because that series that we constructed blows up at s equal to 1 over phi n. This factor also is going to blow up. And this is a contradiction to what we concluded that things should be convergent originally all the way in real particles bigger than or equal to 0. So, sorry, my notes somehow ends here. I cannot continue, but that's, I hope the idea is roughly clear how to finish it. Okay, so thank you. So that's the last part. Now, basically, we are ready to go and prove this primes in arithmetic progression, Dirichlet's theorem on primes in arithmetic progression. And actually, we will find the density of primes that are in this arithmetic progression. Okay, so that's going to be done next week. Thank you. Have a good weekend. Now I'll just end the video. Thank you. Bye.